Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 35. We're going to talk about correlation. We're only going to do one video for this date on this course calendar. So last time we talked about the trinomial and multinomial distributions, and we were talking about discrete bivariate distributions. Now we're going to use some of that to talk about a correlation, and today we're going to, or in this video, we're going to look at the covariance and the correlation. And then we'll look at properties in covariance and the least squares line. Okay. So let x and y have a joint distribution, f of x and y. And this will work for discrete or continuous. So little strange order of the book, but that's okay. So recall that the mean of x, mu of x, is equal to e of x, and mu of y is equal to e of y, and that the variance of x is e of x minus mu squared, which is e of x squared minus e of x quantity squared, and likewise for the variance of y. Okay? We define the covariance of x and y as sigma xy, not squared, sigma xy, or the covariance cov of xy, covariance of xy, and it is the expected value of x minus its mean times y minus its mean. So this is how this is the product of the distances of the point from x, from the mean of x and the mean of y. So you can think about that and see what it means geometrically if you want. Okay? So it's this codependent variation of x from its mean and y from its mean. Okay, and so I can multiply this quantity out, and I get this, which simplifies. So I've got xy, mu of y, x mu of y, mu of x, mu of y. I distribute the expectation across, and remember that the expectation of a constant, like mu, is just itself. And then I can simplify this because e of y is mu of y, e of x is mu of x, and this shows that this is the covariance of x and y. So this is a handy formula to use. Now the properties of covariance. So the covariance of x and y is equal to the covariance of y and x. So just switching the order shouldn't matter, right? And now here's something interesting that you might not have known, that the covariance of x with itself is simply the variance. So the covariance of x equals e of x minus mu of x times x minus mu of x, which is e of x minus mu of x squared. So that's going to be the variance. Now the covariance of x with a constant, a, is 0. And here's something to know, that covariance of x with y plus z. So I take, and it's like a distribution here, or distributing things. I take x with y, and then I take x with z, and I add. So covariance of x comma y, covariance plus covariance of x with z. Now, linear combination of x with y. Again, I take ax with y, and then I take b with y, and so I've got covariance of ax with y, plus the covariance of b with y, but we know that that is a 0 because b is a constant. And then we can pull out a, and it becomes a covariance xy. And these can be proved very easily using the definition of covariance or this derived formula here of the covariance. Then the variance of x plus y is equal to the covariance of x plus y with itself, x plus y. And so again, I can now do a distribution, x with x, and then x with y, and then y with x, and then y with y. And so we have 4 terms here. And so we look at the first one, and this is the variance of x, and this is the variance of y, and these are the covariance of x and y. And so we have variance of x plus 2 covariance of xy plus the variance of y. So that's going to be handy for us in the future. Now let's look at the correlation. We're going to define the correlation of xy as core xy, which is rho of xy or just rho, if we're dealing with 2, is the covariance of xy, oops, sorry, don't know what happened there, divided by the variance of x, square root of the variance of x times the variance of y. Another way to write this is sigma xy over sigma x times sigma y. And I'm going to call this 1. Okay. Now, the properties of the correlation coefficient, and we can prove this using the properties of the covariance. So rho of xy is rho of yx. So it doesn't matter which one for the correlation, it doesn't matter which one is first and which one is second. For a regression line, it does, but we'll get to that later. The correlation of negative x with y is equal to negative times the correlation of x and y. And this comes from the covariance. If I have covariance of ax with y, this is a covariance of x and y. Here, a is my negative 1. So it comes out to the front. And then if I take the correlation of the absolute value of the correlation of ax plus b with cy plus d, that is equal to the correlation of just x and y. And again, you can do this with the definition of the covariance and the definition. Here's the definition of the correlation. So here or here, and of course, for the covariance, you can use the definition of the covariance. So A and C here are called scaling constants, and B and D are called translation constants. And what this says is that the correlation coefficient is invariant with respect to scale and translation or location. So you can move the points, if you shift all the points so that they're here, it doesn't change the correlation. If you stretch the points or shrink the points, stretch x or stretch y or shrink x or shrink y, that's the scale. It doesn't affect the correlation. So having different units are not important. Neither is having different means. That's really important. We will pick up here next time. Please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't do that, email me, but send me a picture of both your work and the problem so I can help you through email. And please be safe, and we will see you next time.